and welcome to my presentation about the performance of ELISA-based analytical methods supporting compliance with gluten-free regulations. I will focus on the internationally accepted reference method and some topics which are important to know when assessing the performance of a method. Therefore, we will first look at the Codex Alimentarius reference method for gluten analysis. Then we will go over to the AOAC official method of analysis for gluten. In this context, it's important to have a look at the meaning of in-cut samples for assays validation. And my last topic will be the results of the third international collaborative study with reader screen gliadin ELISA. The Codex standard for foods for special dietary use with gluten-sensitive people was established already in 1983. However, sensitive methods to determine gluten in foods were not available at that time. 8 years later, in 1991, the so-called SCARIT ELISA were introduced. However, this method was not as sensitive as the today's methods. You see here the limit of quantification was 150 milligram per kilogram gluten, and the quantification of barley was not possible with that assay. Again, 8 years later, the working group of Professor Mendes in Spain introduced a new assay, the R5 sandwich ELISA. At this time, he used for the extraction of food samples ethanol, as it was usual at that time. However, he learned very rapidly that these samples, or especially that heat-processed samples, were not best extracted with ethanol. So therefore, he developed a new cocktail extraction procedure for heat-processed samples, which he introduced in 2002. In this year also, R-Biopharm introduced the first commercial available R5 ELISA, the reader screen gliadin ELISA, to the market. If we look into the publication from Mendes, we see the description of a simple ELISA based on the R5 antibody. Additionally, he describes problems with the extraction of gluten subfractions which are aggregated to the matrix. Therefore, he developed this new cocktail extraction procedure that he describes here in this publication. With this cocktail, he was able to extract the subfractions from gluten quantitatively and got good recoveries. Due to these advantages, the Mendes method became a type 1 Codex method in 2008. The list of Codex methods is the Codex standard 234. Herein you find the description of the gluten-free foods method, the publication that you have seen before, which describes the Mendes ELISA method in combination of R5 ELISA and the cocktail solution. And on the right side you see the Roman 1, which means that this is a type 1 method of the Codex Alimentarius, which describes and defines the gluten amount that is detected by this method. So this means also there is no other reference method available defining the gluten concentration. So the meaning of this first slides is the explanation that the Codex Alimentarius type 1 method is not only an ELISA, it's a combination of an ELISA and a 5 ELISA, for example the brighter screen gliadin ELISA from R-Biopharm, and the Mendes cocktail, which is marketed by R-Biopharm as a so-called cocktail patented. Hence we find in the Codex Alimentarius of a combination of two standards. The one is the standard for foods for special dietary use, which was introduced first in 1983. And then we see a second standard that we looked at before, the Codex Standard 234, which is the list of Codex methods. In this combination, we have both the analysis of gluten and the description and definition of gluten-free foods for special dietary use, because Codex Standard 118 we find some important definitions for gluten-free food. The one is the limit value, the 20 milligram per kilogram. Food which contains perhaps some small concentrations of gluten, but below this 20 milligram per kilogram limit can be called and labeled gluten-free. Only food above this cannot be called, is not allowed to mention it gluten-free. Then we find the definition of prolamins, because the R5 antibody reacts with one certain part of gluten, the so-called prolamins. The prolamins from wheat are called gliadins, therefore the assay from R-Biopharm is called Ridersin gliadin assay. The prolamins from rye and from barley are called saccharins and ordains respectively. You see here also the definition that these gliadins or prolamins in general are extracted with 40 to 70% of ethanol. However, we saw before that Mendes has developed this cocktail solution which is in combination with a 60% ethanol solution the extraction procedure of choice. Then we see that the prolamins are defined as being 50% of the gluten in wheat, rye and barley, and therefore we have to multiply the result from the R5 assay with a factor 2 to calculate from gliadin to gluten. Altogether, this describes the ELISA R5 Mendes method, which is also given here in this standard. And the history of gluten analysis moved on from this time. It did not stop at the year 2008 when the Codex method was defined. We see further developments. If we look at our assay we got in 2012 from the AOSC the status as official method of analysis for foods. At this time there was no definition of foods. Typically all methods detecting, for example, gluten or also allergens from food samples were defined as being able to detect an analyte from food. However, the AOSC decided to change this policy. In 2016, new AUAC guidelines limited the method, the R5 ELISA from R-Biopharm in this case, to rice and corn-based matrices, because when the international collaborative study was made, which was the basis for the AUAC approval, only rice and corn-based food samples were tested. And with the new AUAC guidelines, we had to mention this in the test kit insert. That was confusing to customers using this kit already for many years, not only with rice and corn-based food samples, also with other food samples. We got questions like, are we not allowed to use it any longer? Is the kit not able to detect correctly gluten in other foods? The test is able to detect also in other foods gluten. It is correct in its determination of gluten. And to show this, we started a third collaborative study in 2020 with a wide range of different matrices to demonstrate its wide applicability. In this study, we focused especially on incurred samples. Before we go to the results of the study, I would like to have a short stop at the definition of incurred samples and the meaning of incurred samples. What are incurred samples and why are they so important for analysis? We heard on the first slides about the problems with extracting and analyzing gluten from heat-processed food. And let's go back to our university time, the lessons that we had about proteins and the protein structure. And we learned at that time that we have different protein structures. The primary structure is the amino acid sequence of a protein. So the amino acid chain may fold to secondary structures, the alpha helix or beta pleated sheet. And if we look at the complete protein, it is folded in a three-dimensional structure, which is then the tertiary structure. If we look at complex proteins, which are built up from 3, 4, 5 different subproteins, then we speak about a quaternary structure. Important for analysis is that an antibody that we use in an assay react always with only one specific epitope. Now look at what is going on with food preparation. Then we see here a model of a protein which is in a native conformation on the left side of the slide. It has beta sheets, it has alpha helix structures, it has a three-dimensional structure. However, if we have this native protein inside a food during food preparation, it is processed, which may cause a change of the conformation, which may go along with a loss of structural epitopes. The hardest food processing is a hydrolyzation. In such a protein, we do not have any longer tertiary structure, not even secondary structures are available. We have only the primary structure of the amino acid sequence. And now let's think of antibodies. If we choose an antibody which reacts with this primary structure, and this is what the R5 antibody is doing, then we see that this antibody will react with native as well as with processed and even with hydrolyzed proteins. However, a second antibody, perhaps which reacts with an alpha helix, will not be able to react with hydrolyzed proteins. Perhaps, as in this example here, it may react with native and processed, heat-processed proteins. However, this antibody which detects or reacts with the beta sheet is not able to react and therefore to determine this protein here in a heat-processed food. This is just an example to explain what is going on with food. And I summarize this here in this slide. So we have in the middle ingredients which are perhaps contaminated with wheat, rye or barley. So we have perhaps gluten from these cereals inside our ingredients. And with the preparation of food, for example, pastries, noodles, we have a processing step which will change these gluten proteins perhaps. And additionally, we have to respect that for the analysis, we have to extract these gluten proteins from the food. They are, as we have heard before, aggregated with a matrix. We have to use harsh chemicals to extract it from the matrix because the target of an assay is the protein. The gluten proteins actually here with the R5 antibody, the prolamins, gliadins, saccharins, hordeins, depending on where they come from. Both the grade of processing and the extraction procedure do influence the protein structure and therefore the recovery of antibodies. Hence, we are faced to the situation that a method is not only a certain technology like ELISA. A method is a complex system of the technology, for example, ELISA, the assay calibration, the extraction procedure that is used, the choice of the antibody, and the food processing. We see definitions by the Codex Alimentarius. We should use an ELISA method. It should be used or based on R5 antibody. We have the calibration to gliadin. And we have the extraction procedure described by the Mendez cocktail. However, we do not find a definition for the foods in the Codex standard. There we find only the general word foods. And therefore it's so important for kit manufacturers to test what kind of foods are able to be detected and analyzed with their method. We have already the different conditions as described here, but now we have to know how do this method react with native and heat processed food, for example. Is it able to extract gluten from these matrices? If you think of this, you may not wonder any longer that different methods show different results for the same sample. And that is why it's so important to have these definitions given here. If you use a different antibody, you will get a different results, perhaps. If you use a different extraction method, even with the same antibody, you may get different results. And that is why it's so important to have an harmonization and an agreement to a certain method for getting internationally comparable results. Now, to find out if our method is able to detect also gluten from heat-processed samples, not only from native samples, and from a wide range of different food samples, not only rice and corn-based, we did this third international collaborative study. And before we started the study, we consulted CD patient societies to ask them which foods are important to include in the study, which foods have a high risk of gluten contamination and are relevant for human nutrition. We choose 19 different real food samples, not only dry foods, but also foods with a high level of moisture. And this is a challenge for such a study, because we have to send these samples all around the world. We have included, for example, a fish food preparation. You may imagine that moisture fish is not stable for a long time. We have here a high or big problem with microbial contamination and degradation of this sample. So therefore it was really a challenge to prepare this collaborative study, and we have not done it alone. We had the support of a university in Germany, and this Geisenheim University also prepared independently these food samples, which sent out to the different labs in the world. Here you see an overview what we prepared for this study. On the left side you see more or less native samples, because we have to include also native samples in this study. These samples were only mixed or blended, but also blending is already a kind of food processing. It may warm or heat a sample. On the right side you see really a wide range of different types of foods, from sweets, from pastries to sauces like pesto, to meat, vegetarian alternatives we included, and as you see, fish. Then you see different food processing procedures, heating, cooking, microwaving we included, because there is a publication already from some years ago which was showing that perhaps microwaving has an impact on the recovery of gluten. We could not see this, to say it directly. We did not see any impact or interference of this microwaving procedure with the recovery of gluten. Further on you see that we changed the time of processing from few minutes up to 1 hour, and you see different temperatures. Some foods were processed at 80 degrees Celsius, others were processed at nearly 200 degrees Celsius. So this is a picture what we sent out. 32 different samples which were blinded, were sent out to 14 laboratories all over the world, from Austria, Canada, Finland, Germany, Ireland, Italy, USA. So in total we sent out 900 samples to these labs, which were then there analyzed with a radar screen gliadin assay in combination with the cocktail from Mendes. Results were very good. The AOSC accepts a recovery level from 50 to 200% for gluten from different sources with different foods, because they are aware that the recovery is not only dependent on the assay, it also depends on the metrics that have we already discussed before, and also the AOSC knows, of course, that perhaps in different food matrices the recovery can be different. With our assay, we saw with these different food matrices samples with 60% recovery at the lowest and went up to 130, 140% in maximum. So we were ideally in the range which is given by the AOSC. And therefore, in 2021, we got from the AOSC again the approval for our Gliascreen gliadin ELISA in combination with the cocktail from Mendes, the in-food application. So we showed with our method that it is able to detect gluten not only from rice and corn-based food samples, it is also able to detect gluten in other foods. Here again the picture to remind you that the Codex Alimentarius method is a combination of R5 and the cocktail from Mendes, and this is important to remind you, think of what you are testing. Sometimes you are perhaps in a situation, we have seen before, hydrolyzed food samples, to use a different method. The peptides are too small to be analyzed with a sandwich ELISA. Therefore, we need a setup in a competitive format. So we have also a competitive ELISA for the detection of hydrolyzed gluten proteins in fermented food, for example in beer or starch. And this was also approved by the AOSC, and we got here also the approval as an official method for gluten detection in hydrolyzed fermented food. Sometimes you may just need a rapid result. Then we have here a lateral flow assay, quick gliadin as we call it. This assay is a qualitative method. It does not determine the gliadin quantitatively, but for rapid result, for hygiene testing, you can use the the strips directly for swabbing, as shown here in this picture. For this purpose, it is perfect. You can swab your surfaces where you prepare food. You can swab the equipment that you use for gluten analysis in a lab, for example, and get in a few minutes a result if everything is clean enough for what you want to do or not. So this means you all have to think, what do I have to test? At what point in the food preparation am I testing? Do I test raw materials? Do I test food products? And when does a contamination occur? Is already the raw material contaminated, then the gluten will be processed with the food procedure preparation, so that all the impacts on the gluten happen with this complete food processing. If only the food product is contaminated, then you do not have the influence of these, for example, heating, drying, frying, whatever. So you have the gluten then in a different conformation, and the method that you choose for your analysis should cover all these different situations. Keep always in mind that food processing has an impact on the protein structure and the matrix aggregation. The extraction procedure is therefore also important. With the raw material, perhaps a simple ethanol extraction is sufficient enough. However, with processed food, you need a cocktail extraction best, because everything has influence on the recovery. So this was the last slide of my presentation, and I thank you for your attention and wish you all the best. Bye bye.
So this was our last session or last presentation for the morning, for the day. So I would like to thank Dr. Stefan Schmidt, Dr. Stefan from R-Biopharm in Germany. So Dr. Stefan wasn't able to be live with us today, but he recorded his presentation about R-Biopharm developed ELISA kit used to test gliadin in order to target gluten and gluten-free food. إذا بتحبوا أي سؤال ممكن أنا أكون عم جاوب عن هذا الموضوع خصوصا وعن البرزنتيشن، بس بحب بالختام أذكر بأهمية this session on gluten-free food. مرة تانية بنتشكر حضور الجمعية المصرية لمرضى السيلياك معنا بهيدا السيشن. أضاءوا على challenges وتحديات كبيرة جدا بموضوع الاستحصال على المأكولات الخالية من الجلوتين، وأهمية فعلا تأكيد أو to monitor to control هذا الموضوع يلي هو الاستحصال فعلا وجديا على مأكولات هي خالية من الجلوتين. when we say خالية من الجلوتين نحن بنعني احترام الليمت يلي هي محددة ضمن الكودكس أليمنتاريوس وهي 20 ملغ بر كيلوغرام. من بعدها كان معنا دكتور منى العلان من دولة قطر الشقيقة من وزارة الصحة، مختبرات وزارة الصحة، حدثتنا كمان عن كل التقنيات المستعملة ضمن مختبراتهم، وخصوصا التقنيات الإلايزا-based المستعملة لتحليل الجلوتين في المأكولات الخالية من الجلوتين. والبرزنتيشن from دكتور ستيفان ركزت على الكت، وأنا بهمني أوضح هون الموضوع إنه this kit هذه الطريقة هي الطريقة المعتمدة من قبل ال AOAC International، وهي المذكورة والمعتمدة من قبل الكودكس أليمنتاريوس لتحليل الجلوتين in gluten free food.